All right, let's try number 22. This one, we're trying to find the equation of the tangent line to this curve sine of x plus y equals 2x minus 2y at a particular point, pi comma pi. So in general, when we want to find the equation of the tangent line, it's still true that we need a point on the line, that's the tangent point. And in this case, it was given to us. And then we need the slope, which is dy dx, and that we would need evaluated at the tangent point. And so basically, we need to find dy dx, and again, notice that the function we're given, sine of x plus y equals 2x minus 2y, is implicit, that is, y is an implicit function of x. We cannot get y by itself solved just explicitly in terms of x. So we're going to use implicit differentiation. So we are going to find the derivative of both sides. So the derivative of the sine of x plus y in general is the cosine of x plus y times the derivative of x plus y. The derivative of x is 1. The derivative of y is dy dx. On the right-hand side, we're going to find the derivative there. Derivative of 2x is 2. The derivative of 2y is 2 times dy dx, because once again, y is a function of x. Now, just as before, I want all terms that include dy dx to be gathered together on one side of the equal sign, but I really need to distribute on the left-hand side the cosine of x plus y through the parentheses there. So I'm first going to take the cosine of x plus y times 1, and then the cosine of x plus y times dy dx. And then on the right-hand side, I'm leaving things just as they are. And here again, I want to combine, well, not combine, I want to gather like terms together on the same sides of the equal sign. So all the terms that have dy dx, I want those together on the left. So the cosine of x plus y times dy dx is already there. Then I want to add the 2 dy dx from the right side to the left. And then any terms that don't involve a dy dx, I want together on the right-hand side of the equal sign. So I already have a 2 there, and then I want to subtract the cosine of x plus y from the left side to the right. Then you can see that the method is hopefully starting to become clear of what we do. We want to factor out dy dx from the left-hand side, and that leaves us the cosine of x plus y plus 2. And then our last step is to divide both sides by whatever is being multiplied by the dy dx, because again, I'm trying to find dy dx. So I have that the derivative of y with respect to x is 2 minus the cosine of x plus y all over the cosine of x plus y plus 2. So once again, notice this is different than the derivatives we've had in the past because it includes x's and y's together. Now, in order to find the equation of the tangent line, I need to evaluate that slope dy dx, the slope of the tangent line, at the tangent point. So I need to find dy dx at the point pi pi. Okay, so I need 2 minus the cosine of pi plus pi. Pi is going in for x and pi is going in for y, over the cosine of pi plus pi, substituting pi for x and pi for y, plus 2. So I have 2 minus the cosine of 2 pi over the cosine of 2 pi plus 2. So I don't know if you remember your trig, but the cosine of 2 pi is 1. So the slope of the tangent line is actually 1/3. So just as a reminder, slope of the tangent line, slope of the curve, instantaneous rate of change, that is the derivative. So I want to find the equation of the tangent line, the equation of the line that has slope 1/3 and point pi pi. So using my general form there, point slope form, I have y minus y1 equals m times x minus x1. Now some of you tend to leave the equation that way, and that's okay. Others of you actually write it this way instead. M times x minus x1 plus y1, and that's fine as well. If you wanted to simplify that into y equals mx plus b form, you could do that as well. Okay, I'm going to call this my final answer, and I do have a picture from Mathematica here where I graphed the given function, and I had to use a special command because, again, y is not an explicit function of x, but you can see the tangent line there in orange. That is the line y equals 1/3 times x minus pi plus pi. Right, and the blue curve is the sine of x plus y equals 2x minus 2y. So there's a way that you can tell Mathematica that you want to graph something that doesn't have y solved explicitly for x. And there you go.